This is just a standard cubic equation, but by the end of this video, you will know how this function led to one of the most beautiful things in all of mathematics. We've all seen the quadratic formula, a tool that allows you to solve polynomial equations of degree 2 in one step. You just plug in A, B, and C, and boom, there's your answer. In the late 1400s though, a mathematician named Scipione Faro was working on a solution for the depressed cubic equation. That is, a cubic without an x squared term. When he eventually solved it, he kept it a secret, until on his deathbed, he revealed it to his student, Antonio Fiore. Fiore was much more cocky than his mentor though, and with his newfound knowledge, immediately challenged a much more experienced mathematician, Niccolo Tartaglia, to a math duel. Math duels in this period were very important. Wealthy people would bid on the duel, so not only would the winner receive money, but also fame and potential jobs as a result. Antonio Fiore sent Tartaglia 30 depressed cubic problems, thinking that he was the only one in the world who knew how to solve them. Unluckily for him, Tartaglia worked out his own method to solve depressed cubics. He solved all 30 of his problems, while Fiore solved none.
Eventually, this formula was discovered and published by a man named Girolamo Cardano. While toying with his formula, Cardano realized a flaw. When you plug in a modified version of the equation, x cubed equals 15x plus 4, you would arrive at a step that involved the square root of negative numbers. Normally, this would be written off as just having no solutions, but we know that cubics always have one real root because of their shape. So, another mathematician, Raphael Bombelli, decided that he would just use them in that intermediate step, because they would cancel out later. Eventually, Leonhard Euler decided to use notation I for imaginary numbers. Another thing came out of this though, the representation of complex numbers on a plane, having the imaginary axis perpendicular to the real axis. In this way, complex numbers are expressed as a coordinate. This point is 1 plus 0i. This one is 0 plus 2i. And this is 2 plus 3i. The natural next step is plotting those points on a graph function. With a complex input and a complex output, there's a problem here though. In order to have a complex input and a complex output, you would need a 4-dimensional graph to represent the information for all 4 axes.
In the 1980s, a mathematician named Frank Ferris thought of an ingenious way to graph these functions without losing any information, and it was by using color. We do this using HSB, which stands for hue, saturation, brightness. The hue is the angle of the complex number away from the x-axis, going counterclockwise, otherwise known as the argument of the complex number, and the radius, or modulus, determines the brightness, while the saturation just remains the same. Imagine drawing a line from the origin to the point, like the arm of a vector. Now, just draw the angle between the arm and the x-axis. To find this angle, we just take the height of the point, or the imaginary part, and then the x distance, or the real part. Now, you can use tan inverse of the two sides in order to find the angle of the point. And you can find the radius by just using the Pythagorean theorem with the same parts. To actually graph these functions, we first start with the input point. Now, the input point is just the same as we'd graph a regular complex number, just a number in the complex plane, and you can see that we have both the axes for the input numbers, but it gets a little bit different for the output numbers. The output numbers are in the same point in space as the input numbers, but are colored based on where the output number would land. Look at the graph shown. You can see that I is colored cyan. But cyan in the original colorway, as you can see in the top right, is reserved for the negative real numbers. And as we know, I squared is -1. So rather than I ending up where it should be, it is colored based on where its output ends up. And that's how they condense these extra dimensions for the output numbers. These graphs can be extremely important in complex analysis, whether or not you're trying to see if poles are in a range for using Cauchy's residue theorem, or if you want to graph important functions like the Riemann zeta function.